Hello, my name is Lutz Warnke, and today I'm going to talk about some joint work with Nick Wormold, which lies at the intersection of combinatorics, probability, randomized algorithms, and percolation theory. So what is the model that we're studying here? The model that we're studying is the so-called random D process, which you should think of as a degree-constrained version of the classical Erdős-Rényi random graph process. So the idea here is that we're going to start with an empty graph on n vertices, so we're looking at a finite number of vertices, and then in each step we're going to add one random edge to this graph so that the maximum degree stays less or equal than d. In other words, we add random edges one by one, subject to the constraint that we never ever create a vertex of degree larger than d. Also note that here in the finite graph setting we have n vertices, and we're not looking at lattices here, but in principle any two vertices can interact. What is our main result? Our main result is that there's a phase, that this process undergoes a phase transition with respect to the giant component phenomena. In other words, what we're going to show is that there's a critical point around which a linear size giant component, a component with order n many vertices, emerges. And the relevance here is that if your graph has n vertices, so a giant component of linear size really corresponds to a macroscopic object. And what we show is that there's a critical time if we go for a situation where all the components have size little of n to a situation where we have one linear size giant component of order n. There's some analogies with percolation theory that I would like to point out. So on the one hand, clearly you can think of the random D process here as some kind of percolation process with degree constraints, come here from this maximum degree at most D. And in the context here of random graph theory with a finite number of vertices, you should think of the giant component as an analogy of the infinite cluster. Okay, so this really corresponds to kind of the key phase transition in this model. One of the things I wanted to advertise with this talk is that even in this finite random graph setting, we can show some nice further analogies. So in particular, we can show the equality of two critical points in this model. In this case, that the location of this giant component phase transition equals to the blow up point of the susceptibility. This really mirrors these classical results by Eisenman, Barsky, and Menchnikov from the 1980s, where they show these kind of results for infinite lattices. Okay, I think it's a good time to again look in more detail as an example of this random D process. Remember the random D process, we start with an empty graph and vertices, say these red dots here, and then in each step we're going to add a random edge to the graph subject to the constraint that the maximum degree stays at most D. In other words, that we never ever create a vertex of degree larger than D. So let's look at a quick example where the degree constraint is 3. So we start adding more and more edges to the graph, but so far nothing happens. So far every vertex here has degree at most 2. So these are still in the game. But at some point what happens is that when we add another edge here, we get an inactive vertex because this has now 3 neighbors. Okay, and the point is that inactive vertices, those of degree here, in this case degree 3, they're out of the game. We never ever can add any more edges to them. Okay, so as we continue adding more and more edges, then you'll see that more and more of these inactive vertices arise. And the analysis of this random D process is really complicated by the fact that the set here of active vertices, the set of vertices to which we can still connect with edges, changes over time. In other words, we have some process with some non-trivial dependencies and constraints, which complicates the analysis. Let me say one or two more remarks about this model. So, first of all, in a graph with n vertices, the degree can never be larger than n, or in fact n minus 1. So if you set this degree constraint D here to n or n minus 1, then you actually cover the classical Erdős-Rényi random graph process, where in each step you just add a new random edge. I would also like to point out that there are many variants and generalizations of this process, many of which we can also handle. One perhaps very attractive one is the following. In this random D process, every vertex can have degree at most up to a degree D. But you could also imagine a situation where, say, half of the vertices have degree constraint 2, the other half have degree constraint 3, and we can still analyze such processes as well. So you might ask yourself, so why should we care about this process? So first of all, I think it's an extremely natural algorithmic model if you try to generate, for example, regular graphs, because what we're doing here, it's really just a random greedy algorithm, which in each step tries to put down a random edge without violating this degree constraint. Okay, so we try to jam in as many edges as possible in a random way. And indeed, this kind of deep process has already been studied since at least the 1980s in the mathematical chemistry literature. So from a random graphs perspective, this random deep process is very interesting because due to this degree constraint here, we get some non-trivial dependencies between the edges, because if you put a certain edge down in your graph, then this will forbid certain other edges and so on and so forth. So this process really provides a convenient testbed for improving the methods of analysis that we have, so that we can go beyond the classical case where the edges are just added independently, for which we by now have pretty good control. The third motivation here is the existence of the phase transition, perhaps surprisingly, was still open prior to our work. So this was first raised, I think, in 1997 by Nick Wormold. Okay, so what is our main result, or a simplified version of our main result? So basically we show that there's a phase transition where you go from a situation where all the components are relatively small, say at most logarithmic in size, to a situation where, like this, where you have this one big giant component which contains a constant fraction of all vertices in the graph, and everything outside that large component is again much smaller. Okay, so in particular, when the degree constraint d is at least 3, we show that there's this critical point Tc around which this transition from everything small, the subcritical phase, to one big giant component, the supercritical phase, around which this happens, around this critical time Tc. And one way to formalize is to say, okay, let's look at the size of the largest component after t times n many steps. And we show that with high probability, meaning with probability tending to 1 as the number of vertices n tends to infinity, with high probability, this large component size logarithmic in n if t is smaller than Tc, so we're in this situation. And the largest component is linear in n, and t is bigger than Tc, and we're in this situation, okay? And the relevance again is that logarithmic in size means much smaller than the total number of vertices. Linear in size means a constant fraction of all vertices. So the point here is, so first of all, this result resolves this problem of Wormold from 1997. And you might wonder, so why do we have this d at least 3 here? Well, the reason is simply because the other cases behave differently. We can also analyze them, but I don't want to discuss them too much here in this 10-minute talk. So the point is, when d is equal to 1, every vertex can have has degree at most 1, so all components have size at most 2, so there is no phase transition. For d equals to 2, something more delicate happens. So what happens is that if you look, for example, at the d2 process, at the end, you see that the size of the largest component has a non-trivial limiting distribution. Okay, but I don't want to say too much about this in this talk here today. Let me again highlight these analogies with percolation theory. So you should think of the result that we have these two phases, a subcritical and supercritical phase, and you should think of maybe the size of the largest component rescaled by n as your order parameter. In the subcritical phase, this order parameter tends to 0 as n tends to infinity, and the supercritical phase, this order parameter tends to some non-zero value as n tends to infinity. One thing I would like to highlight is that our proof shows that this critical time Tc has another nice description, namely that the location of the phase transition equals the blow-up point of the susceptibility. At this point, you might wonder, what does susceptibility mean for a finite graph? After all, in classical percolation theory, we can just talk about the expected cluster size at the origin, but when we talk about finite graphs, we do not anymore have this kind of symmetry or translation invariance, so we need to come up with a new notion of susceptibility. And here's one very established one. So we look at say, some finite graph G, and susceptibility is just the answer to the following experiment. We're going to sample a random vertex from our graph, so each of the vertices will be included with probability 1 over n, and then we want to say, okay, what is the expected cluster size of the component containing this randomly chosen vertex? And this is exactly what the susceptibility is defined, okay? The expected size of the component size of a randomly chosen vertex. The caveat here for the D process is that the susceptibility is not really the parameter we want. Remember, we discussed that active vertices are kind of out of the game. You can never ever connect to them. Inactive vertices are out of the game. You can never ever connect to them. So only these active vertices matter. So only the vertices of degree at most D minus 1. And so we, in the proof, instead of the susceptibility, we actually look at the so-called active susceptibility, which is kind of the same as the susceptibility, just that now we just focus on active vertices. So it's the expected number of active vertices in a component containing a randomly chosen active vertex. This is their notion of active susceptibility. So in the proof, this active susceptibility, it's not so easy to analyze. One of the difficulties is that to even track or recover the active susceptibility, we need to introduce a large number of auxiliary random variables, order d squared many auxiliary random variables. And as you can imagine, when you have so many variables, it's not so easy anymore to analyze when does this have a blow-up point, etc., etc. Nevertheless, it is, in fact, a key step of our proof that we show that the active susceptibility blows up. In fact, we can show the susceptibility and active susceptibility both blow up at the same point TC, and then our proof shows that after TC, in fact, you get a linear size giant component. Okay, so this is kind of what I want to say about the proof, and here let me just summarize. So we're looking at this random D process, and our main result shows that there's a critical time TC around which a giant component emerges, at which you go from a situation where all the components are small to where one macroscopic giant component emerges. And throughout this talk, I tried to highlight this nice interplay between, say, this random graph theory and percolation theory. In particular, I want to highlight that we have this result which shows the equality of two a priori different critical points, namely where the phase transition happens and the blow-up point of the susceptibility. I hope that we're going to have a preprint of this result up on arXiv in a month or two. Thank you very much for your attention.